Hello everyone, welcome to our webinar today with NVIDIA entitled How Can Students and Researchers Use GPUs with Ease? My name is Sam Watto, I'm the Sales Manager at Boston. Joining me today is Paul Graham, Senior Solution Architect at NVIDIA. So, Boston is NVIDIA's largest and most highly accredited elite partner in Europe, including accreditations in DGX and HPC, virtualization, visualization. We also have multiple licensed engineers to provide deep learning training within NVIDIA's Deep Learning Institute program. Boston is ATP program accredited, as well as being a leading OEM solution partner in EMEA. Boston also has installed and supports multiple deep learning appliance deployments in EMEA as well. So our locations are shown here. We're actually part of the 2CRSI group, so we have a global footprint with production facilities serving our global customers on a local basis. Boston has leading lab facilities in several locations, offering services in research and development, so cluster design and implementation. We can benchmark and verify performance across multiple hardware stacks. Boston offers prospective and existing partners and customers testing on the latest technologies with over $1 million of equipment based on existing and pre-released hardware. The lab is available on an anytime remote dial-in basis. From a services perspective, we welcome everyone to leverage our expertise, whether through site visits, benchmarking, ongoing support, and also maintenance. Boston has a comprehensive suite of HPC services, including an HPC profiling center, HPC managed services, cluster validation, integration, and project delivery. We work with our customers and their customers to develop a customized solution and service package that fits their needs. So we are proud to offer the NVIDIA Deep Learning Institute as part of the Boston Training Academy. Our in-house data scientists follow the DLI curriculum to offer your staff and customers training on everything from the fundamentals of computer vision for people with familiarity with basic programming fundamentals, through to deep learning for autonomous vehicles for people with greater experience with CNNs and C++. Whatever your starting point, the BTA and DLI courses have courses to fit your requirements. After the webinar, we'll share further details of courses with you via email. Just onto a quick case study. So why are we speaking to you today? Well, Boston has a strong presence in the research and life sciences space. Just one example is our work in partnership with NVIDIA. We are building out optimized solution stacks for the next generation of DNA, RNA sequencing technology. This technology is increasingly being used by scientific researchers analyzing many thousands of genomes to better understand genetic diversity and discover new variants. Sequencing is also being increasingly adopted to generate rapid insights in healthcare settings, food safety, or environmental analytics. Just a reminder, this is a live webinar, so you can submit questions to myself and Paul at any point via the Q&A tool as displayed on the screen now. We'll answer during a Q&A session at the end. So now to hand over to Paul at NVIDIA.
Hi everyone. So good morning. I hope you're all well. Thank you for inviting me to this from our colleagues from Boston. Always good to speak with them. My name is Paul Graham. I'm going to just switch off my camera for saving bandwidth. I just thought I'd put it on first of all to say hello. I'm a solutions architect with NVIDIA, focusing on higher education and research in the UK. As an SA, I provide advice on GPU hardware, but my main job is to provide training, but also to raise the awareness of researchers to ensure that they can make the best use of that hardware via the software, libraries, applications, and frameworks that are available from both NVIDIA and the broader university community. And that's the focus of today's webinar. I'll go over our latest A100 GPU hardware and some of the features in the Ampere architecture, which make it a really powerful tool for accelerating research, especially for AI and data science activities. We'll then look at some of the ways that researchers can deploy the A100 at the departmental level, be it in a high-powered workstation or a single DGX server appliance. Following that, We'll look at how we can ensure that we make efficient use of those GPUs, both in terms of supporting multiple researchers and students on a single system, but also performing deep learning training or complex simulations at scale across multiple GPUs. We'll conclude with an overview of some of the software, libraries, tools, and frameworks which make sure that the GPUs are straightforward to use and that the researchers can focus on their research. Many researchers already using GPUs make use of centralized resources, such as a campus HPC cluster or run experiments in the cloud. Whilst these are great ways to get access to substantial resources, there are also challenges with these approaches. For the centralized cluster, it's a shared resource for hundreds of users, so access may be limited by the queue system. For cloud, it is very flexible, but can be hard to manage the usage accounting across users and projects. A solution to this is to have dedicated resources at the departmental level. These will enable access on demand within the lab with full control over the use of the system. And with modern GPUs, even a single server can provide a hugely powerful resource to multiple users simultaneously. Before we dive deeper into the hardware, let's look at some of the challenges that we are seeing in research centers. One of the main difficulties is that computational workloads can vary by huge amounts. One day you may be providing multiple development environments for researchers. The next day you may be running a complex simulation across multiple nodes. Focusing in on AI, as the applications of deep learning proliferate, so does the complexity of the neural networks, with modern networks achieving greater accuracy but having exponentially more hyperparameters than previous generations. As such, more and more compute is needed to train these models, so this requires dense, powerful nodes with multiple GPUs connected together in order to minimize the training time. But if we also consider deployment of our applications which are making use of inference for those trained networks, then workload looks very different, with hundreds or even thousands of smaller computations where low latency is critical. Going beyond AI, a single departmental system may well have to support vastly different workloads, such as running a teaching session for multiple students, or performing intense multi-GPU computations to generate results before a paper deadline. So the challenge is, how can we provision resources which can support both these extremes, but also maximize utilization so that devices aren't sitting idle? With this in mind, let's look at the new A100 80GB GPU, which enables researchers to tackle the most important scientific and big data challenges. Already the world's highest performing GPU, the NVIDIA A100 now comes with double the high bandwidth memory at 80GB, allowing larger simulations or more complicated neural networks to be tackled within a single device. This is supported by up to 2 terabytes a second of DRAM memory bandwidth, which is the world's highest memory bandwidth to beat the world's fastest GPU. The A100 is built on our Ampere architecture that has the third generation of tensor cores, which provide dedicated hardware to accelerate the matrix multiply and accumulate calculations, which are at the heart of deep learning applications and indeed many HPC simulations. It also has the third generation of NVIDIA NVLink, which provides direct high-speed communication between the GPUs, improving performance for multi-GPU calculations where data needs to be shared across devices. And we have the new multi-instance GPU that partitions the GPU into smaller isolated slices for more effective utilization. And we'll look a bit more in depth into that later. The ability to partition the GPU into small instances or to connect the GPU with others to create a larger compute infrastructure means that A100 is perfectly suited to provide the flexibility to meet the changeable workloads required by modern research centers. There are various servers and configurations available for the A100. We'll take a look at a couple of them now. This one is the DGX Station A100. It's designed as a standalone workstation for a lab or a department, which can sit under your desk, but has massive compute power with 4 of our A100 80GB GPUs connected via NVLink. It is liquid cooled and can be plugged into a normal socket in an office, in a lab, or even at home, with no additional IT support or investment necessary. It also comes with over 7 terabytes of onboard NVMe storage, which can be used, for example, as a cache for storing training data. With the multiple position support that the tensor cores and the GPUs provide, this workstation can deliver up to 2.5 petaflops of FP16 AI training, or indeed 5 petaops of int8 inferencing, making it an incredibly powerful AI appliance which can be installed anywhere. And with multi-instance GPU, it can be straightforwardly used to support multiple users or activities. From the server side, we have the new DGX A100 640GB system. This has 8 of the 80 gigabyte A100 GPUs on board, all connected via NVLink, but also NV switch technology, which maximizes the bandwidth available between the cards, which is great for multi-GPU deep learning training, where network weights need to be regularly shared between epochs. And to support the large data sets used in deep learning, the DGX has 30 terabytes of high-speed NVMe storage, so the data can be stored next to where the compute takes place. Each of these DGXs comes with 10 NVIDIA Mellanox ConnectX-6 network cards. This ensures performance will scale well if calculations are extended across multiple nodes. On the subject of scaling up from one node, we actually have reference designs which prescribe how to deploy multiple DGXs with all the necessary networking and storage, making it as straightforward as possible to scale your system as your demands increase. Indeed, this reference design is used internally at NVIDIA, for example, in our Selene system, which is currently 5th on the top 500 list of the world's fastest supercomputers. And also the new Cambridge One system, which you may have heard about, which is being installed in the UK for life sciences research. Note also that thanks to the hardware and software innovations employed in our GPUs and our networking products, they are extremely energy efficient. The #1 spot in the green top 500, which measures energy efficiency of these systems, is currently held by an NVIDIA DGX-based system, and that delivers over 26 gigaflops per watt. So let's take a closer look at one of the most interesting new features introduced in the A100, multi-instance GPU, for which I've got a short video demo. Okay, if we think about how we utilize GPUs in the higher education environment, workloads will change over time. Sometimes you'll want to perform complex simulations or visualizations, as for the example showing now, which will utilize several of the GPUs to work in tandem, or indeed if we're doing deep learning training at scale. At other times, you'll want to be able to support multiple researchers doing development work, interacting with GPUs via Jupyter notebooks, or testing and developing software via IDEs or even the command line. Or you may be running a teaching lab where each student needs a dedicated GPU. So the A100 Tensor GPU maximizes the utility of every GPU in the data center to meet different sized acceleration needs, from the smallest job to the largest multi-node workload. While many HPC and AI workloads continue to scale in both size and complexity, some workloads aren't as demanding, such as early scale development and small batch inference. To help researchers to handle this wide spectrum of accelerated workloads, the A100 offers a new feature called multi-instance GPU, or MIG for short. MIG allows administrators and resource managers to partition each A100 into as many as 7 individual GPUs. Each MIG GPU is fully hardware isolated, providing dedicated compute, memory, and memory bandwidth. For system admins, MIG enables the department to offer a greater number of custom-sized GPUs to users, thus keeping the utilization high. Let's dive in and check out MIG running a set of HPC and AI workloads on a single A100 GPU. In this example, we've configured 4 MIG devices. The first contains 4 slices with 56 SMs and 20 gigs of memory. The remainder of the GPU is split into 3 instances, each containing 14 SMs and 5 gigs of memory. Next, we'll launch a series of jobs. On the larger 4-slice MIG, we'll run a molecular dynamics simulation of the APOA1 protein in the popular NAMD software package for studying large biomolecules. On one of the single-slice MIGs, we'll kick off a computer vision inference workload, which is classifying images of flowers. On the other single-slice MIG GPU, we're running an active debugging session where the user can step through their code line by line in an IDE to help simplify development. On previous generations of hardware, this workload would require 3 full GPUs. However, using A100, we can handle the set of work on a single GPU with a MIG slice to spare. So to recap, each instance has its own dedicated cores for compute, dedicated memory, and dedicated memory bandwidth to ensure a consistent, high-quality experience for the user. As we've shown, the instance sizes are flexible, so you could create one instance using half the A100, for example. And on the A100 80 gigabyte, the smallest instance size still provides 10 gigabytes of the high bandwidth GPU memory. So these are certainly not insignificant resources. On a DGX A100, we can support up to 56 of these instances. There's 56 different user scenarios, but also via NVLink and NV switch, we can treat the DGX effectively as a single device for when you need the maximum performance for training or simulation. Similarly, for the DGX station we saw earlier, up to 28 different MIG instances can be supported at one time. Another example of usage of this, Boston and NVIDIA contributed an HPC task to the recent CI UK Student Cluster Challenge competition. So Boston provided access to a DGX A100 with 8 of our GPUs, and we had 4 student teams, so each team got 2 GPUs. We set up those GPUs, one in multi-instance GPU mode, so each team member could have a small MIG instance to work on the problem via Jupyter Notebook, and the second GPU for each team was kept whole in order to perform the benchmarking. In order to make it as easy as possible for users to straightforwardly and efficiently make use of GPUs, NVIDIA puts a huge amount of effort into software. In fact, this may surprise some of you, NVIDIA has many more software engineers than we do hardware engineers. We'll now take a look at some of the ways that researchers can quickly and easily exploit the hardware innovations on our GPUs via the software. Typically, when users first come to GPUs, they make use of applications or frameworks which have already been accelerated, such as GROMACS in the life sciences, or TensorFlow or PyTorch in deep learning. This can make it a smooth experience as those applications already have GPU support built in. But what if you're developing your own code? In the first instance, one might consider using libraries such as BLAS for linear algebra. The good news is that for many commonly used libraries and operations, there are GPU equivalents which can be slotted in as replacements with minimal effort on behalf of the developer. Here we have a few examples of the libraries available, such as QSparse for sparse matrix operations, and also our new QTensor library for higher dimensional matrix operations. The key thing I'd like you to take away from this is that we put a huge amount of effort into making sure these libraries can straightforwardly exploit the new features in each generation of hardware. For example, as mentioned earlier, we have the new 3rd generation of tensor cores in the A100. These provide support for new data types such as double precision and bfloat 16, or our own TensorFloat 32 data type, which has the range of single precision but the accuracy of half precision, which is perfect for mixed precision training for deep learning. The libraries have been expanded to exploit these data types seamlessly, making it really easy for a developer to utilize the power of the tensor cores and deploy highly performant code. On the subject of performance, how do we ensure that we're getting the best out of the GPUs? Well, there are a few tools which can help with this. Firstly, we have the Nsight performance tools. These allow developers to analyze applications at both the system level and the GPU kernel level, giving insight and advice on where there is potential to improve performance so that programs can be further optimized. We also have plugins for integrated development environments to allow programmers to develop in an environment they are already familiar with. At the system level, we can look at resource usage and system health via the Data Center GPU Manager, or DCGM. This simplifies administration of GPUs and can perform a variety of functions, including active health monitoring, diagnostics, policy management, group configuration, and accounting. And it can be used as a standalone tool, for example, via the command line, or metrics from DCGM can be exported into other tools such as Prometheus or Grafana for visualization. As well as libraries and accelerated applications, we have over 80 frameworks targeted at particular fields, with the aim of making it as easy as possible for researchers to develop and deploy their own solutions and minimize time spent reinventing the wheel. I'll touch on a few of them here, but just a note, any text underlined in green is actually hyperlinked. So we'll share a copy of the slides after the event. You can access these and any I don't cover today. First off, we have Rapids, and I know Boston are going to say something about this later as well. For those of you familiar with data science workflows, you'll be aware of Python libraries such as scikit-learn for machine learning algorithms such as XGBoost, or the Pandas data analysis library. What Rapids does is it provides drop-in accelerator replacements for those libraries, enabling the entire data science pipeline from extract, transform, and load operations through to post-training analysis to be performed orders of magnitude faster on the GPU. This frees up the data scientist to focus on interpreting results and adding value to the science rather than waiting for their data to be prepared. In Clara, we have a suite of SDKs and tools to assist in healthcare. These include pre-trained models for image classification and segmentation, AI-assisted annotation for labeling medical scans. We have our Parabricks software for genome analysis, and Biomegatron, which is a natural language processing neural network model used to analyze research literature. SimNet is one of our newer offerings, which provides a framework to make use of partial differential equations, PDEs, along with their boundary and initial conditions, to create neural networks informed by the physics, by the equations themselves, rather than data. So I think this is really interesting new innovation, and this is now available via our early access program. Omniverse is a collaborative platform for visualization with complex workflows, such as visualizing and interacting with the simulation whilst it's running on a remote system. And some of the visuals you saw in the demo earlier were created within the Omniverse environment. Isaac is a toolkit for the development and deployment of robotics, and we'll now look at a demo of one of the features of Isaac in action, Isaac Gym. And what Isaac Gym does, it allows us to create a physics simulation environment where robots can train via reinforcement learning. So reinforcement learning is one of the most promising research areas in machine learning, and robotics has already been used to teach a robot hand to solve a Rubik's Cube, or a robot to learn movement by imitating animals. We can use virtual environments to help train robots using RL. And as they are virtual, we can, for example, control the lighting to simulate different times of the day, or easily put additional obstacles in the environment with realistic physical properties to represent complex factories. Perhaps most importantly, though, we can populate the environment with many of these robots at the same time, or run tens of thousands of these environments simultaneously on a single GPU, greatly reducing the time to get to a trained robot. And Isaac has a Python API, which makes it straightforward to use, and the environments can be observed even from within a Jupyter notebook. The frameworks and platforms we've looked at are typically available as standalone GitHub repositories, but for many of them, we have containerized versions using technologies such as Docker or Singularity. And these are ready to go via our software repository, NGC. As well as our frameworks, NGC also hosts GPU-accelerated containerized versions of all the major deep learning frameworks, such as TensorFlow and PyTorch. It's worth noting that we have ongoing effort into continuously optimizing our libraries and software, and these frameworks in particular are regularly updated. So even if you've already downloaded TensorFlow, for example, it's worth checking back to see if there's a more recent version. And this will ensure you continue to get the full benefit of your GPU hardware throughout its lifetime. As well as frameworks, we have various model training scripts to help get started with AI. We have example workflows for various applications, such as medical imaging. And we have over 60 pre-trained models, which can be used as a fantastic starting point for transfer learning or retraining with your own domain-specific data. For those of you interested into a deeper dive into programming for GPUs or training and deploying AI applications, we have our Deep Learning Institute courses, and Boston have already mentioned that. They are a certified partner for delivering DLI courses, so please get in touch to see what courses they are running soon. We also have our University Ambassador Program, where interested candidates at higher education institutions can become certified to deliver the courses themselves to their institutes. We have a wealth of ways for developers to engage and gather more info from us, and I've included a lot of the links here. A couple of these I'd like to highlight are our in-depth technical how-to blogs. They're a really good resource, and we have lots of examples of how to get going with the different programming paradigms or with some of the different frameworks that we supply. So there's some great examples there. We also have our GTC on-demand content. I'll say a little bit more about GTC in a moment, but basically these are all the presentations which were recorded from previous GTC conferences, and they're available to view. And again, there's lots of presentations there on some of the frameworks which we've looked at today. Also, we have a new technical overview document, which looks at enabling enterprise AI with GPU integrated infrastructure. And that gives you some great ideas for how you can set up your departmental systems to support all the different activities which are going on. For other resources available to academics, we have our developer teaching kits, which include free access to online training for students. So what happens here, you have your lecturer, your professor can request these, they can incorporate these into their courses, which they provide for their students, and they can teach their students how to take advantage of GPUs. We also run various academic workshops, so there's a link there for that. We have boot camps, so these are usually 2-day tailored training events, typically for a target group. For example, we can provide open ACC training or AI for Science, which is one of the new boot camps we offer. And there's a couple of these AI for Science boot camps coming up over the next month or so. So again, there's a link there you can click on to register if you're interested in those. And we have our in-depth hackathons. These are they used to be sort of 5-day in-person events, because we now run them virtually. So they take place over a slightly longer period, but they're slightly less intense. And what happens here is the idea is people come with a particular code, a particular application they want to develop further on GPUs. It may already be running on GPUs, or they may be the first time they want to get it running on GPUs, and they spend a week or so with a couple of mentors, one of whom is usually from the NVIDIA dev tech team, who are basically our CUDA ninjas, and they work very closely with them over a week and work in depth on that code. And it's a very positive experience usually for everyone involved. The next one is happening in the UK, is at EPCC. It's running between April 19th to April 28th, and so I believe registration is open for that now. So again, there's a link there which you can click on and investigate that further. Before I conclude, I'd just like to mention that we have our next GPU Technology Conference happening in April. Again, it's a virtual event, so very easy to attend. And there will be many interesting talks, including some on some of the technologies and frameworks we've touched on today. Most of the talks are recorded, so it's searchable and available after the event. As we saw, there was a link earlier for that. So it's really worth visiting the site to see talks from previous GTCs. So recap what we've seen in today's webinar. We introduced the A100 80GB GPU and some of the DGX appliances optimized for AI and deep learning research. We saw how these GPU systems are very flexible for the differing workloads that are seen day to day in a research department, with features such as NVLink for efficient training or simulation using multiple GPUs, or MIG, multi-instance GPU, for slicing the GPUs into smaller instances for more lightweight applications. Then we looked at some of the software available to make sure that GPUs are straightforward to use so that researchers can focus on their research and not so much on the tools that they're using. And finally, we covered some of the resources and ways to get more information, be it training via the DLI courses, access to teaching materials for university researchers, our various online repositories, or engaging with our events such as hackathons or conferences. Just to remind you, this deck will be shared after the event, but also feel free to contact myself or Boston if you'd like more information on anything I've covered. I'd be more than happy to help with that. And I'll hand you back to our host. So back to you, Sam. Thank you.
Thank you very much, Paul. Okay, so just a reminder more than anything else, back to the Boston Labs section here. So Boston has the entire range, I believe, of NVIDIA DGX products within the lab, so including DGX A100, DGX2, as well as a suite of Supermicro-based NVIDIA server products as well. So these are available on a testing basis, and we can make them available via VPN to interested parties. So please do get in touch should you wish to test. I mentioned earlier the Boston Training Academy and the NVIDIA Deep Learning Institute. I wanted to make you aware of a particular DLI course we run, which can help you build on what you've heard today, Fundamentals of Accredited Data Science with Rapids. So the course can be delivered remotely and lasts a full day, and is delivered by a certified DLI trainer. For more information, do get in touch with us after the webinar or leave your email address in the comments and we'll contact you directly. So moving on to the Q&A, I'm going to pose some questions to Paul now. Hopefully that's okay. So Paul, how easy is it to make the most of the MIG mode?
Okay, so it's very easy. So you can do it via the command line itself. So those of you familiar with the GPUs know there's the NVIDIA SMI commands, which allow you to investigate what's happening with your GPUs. You can just use those to create MIG instances straightforward. You can create them and destroy them using that. Also, MIG is integrated with Kubernetes, so you can use that to deploy your containers on MIG instances. We're also investigating adding Slurm support to MIG as well, because obviously that for many of our customers that's very important. So we're looking into how we can provide that as well. But it is very straightforward. Once you've enabled your GPU in MIG mode, you don't need to. You can just create MIG instances and just destroy them very straightforwardly, as long as there isn't anything running in one of the instances. It does require a GPU reset to put it into MIG mode, but that's very easily done as well. So yeah, it's very easy to use.
Okay, perfect, thank you. And how much does it cost to access Rapids?
So Rapids is free, it's open source. So yeah, it costs nothing. And just to say, pretty much all the software which we provide, the GPU accelerated version of our software, is free. The ones which aren't free are ones which you would need licenses for anyway, such as VASP and things like that. You need to buy a license for that. But anything that we provide, like the TensorFlow frameworks and PyTorch frameworks, are all completely free.
Okay, excellent, thank you. So another question we have here is from a hardware perspective, what are my options?
So it depends what you're doing. So we've shown a couple of the configurations that you can buy A100 in. Of course, there's many other different server configurations. There are also PCIe versions of the A100 GPUs, so you can just have 1 or 2 or 3 in a server if that fits your requirements much more easier. The ones we've shown are the DGX systems, and you do get some additional support from NVIDIA if you do buy a DGX-based system. But of course, you get fantastic support from our partners such as Boston as well if you buy GPUs from them.
Sure. Okay, thank you. And the last question is, in the past, the term vGPU has been mentioned. Is MIG the same, or is it a replacement for that?
Well, no, it actually works in harmony with that. What the thing is that virtualization of GPUs, the way that approach works, it has a sort of time slicing effect. And whilst it usually works very well, there is potential for a little bit of contention between multiple users on a single GPU. What MIG does is actually provide hardware support for separation of instances on the GPU. So as I mentioned earlier, each MIG instance actually gets its own dedicated compute cores, its own dedicated part of the memory, its own dedicated part of the cache. They're complementary. If you have MIG mode, you can run virtualized instances on a MIG mode, on a MIG instance, and vice versa. So it's they're definitely complementary technologies. They're not a replacement.
Fantastic. Okay, thank you very much. So just a reminder to everyone, in terms of the Q&A tool, there is a speech bubble symbol at the top of the screen with a question mark inside that. If anyone would like to ask any questions of either of us, please feel free to. In terms of feedback, we'd love to know some feedback. It's always good, useful, very, very useful for us to kind of learn what people think. So do let us know what content would be interesting for you. Obviously, you can do this via the Q&A tool also. We actually have a follow-up mail shot going out as well, so you're more than welcome to reply to that too. So unless anyone has any questions that have come in via the Q&A, we'd like to thank you very much all for your attention, and thank you all for joining, and we'll look forward to speaking to you again soon.
Thanks, everyone.